Now we're going to discuss the second method. To illustrate why you would want another method, let's look at groups of order 4125. This factors as 3 times 5 cubed times 11. Now, based on our strategies from method 1, there's at most one prime with a power greater than 1, so it looks like counting elements should work as a strategy. So let's compute the number of CeLO 3 subgroups and the number of CeLO 11 subgroups. So we see the number of CeLO 3 subgroups has to be congruent to 1 mod 3. It has to divide 5 cubed times 11. Unfortunately here, 5 is congruent to 2 mod 3. And 11 is congruent to 2 mod 3. So any product of these two numbers is going to be congruent to 4 mod 3, which is 1 mod 3. So we're going to see that 1, 5 squared, 5 times 11, and 5 cubed times 11 all have this feature, that they're congruent to 1 mod 3. So there's unfortunately a lot more than one option, or two options. Similarly, the number of CeLO subgroups, 11 subgroups, is going to either be 1, or it's going to turn out it has to be 5 cubed times 11. And for completeness, the number of CeLO 5 subgroups is going to either be 1 or 11. Although normally for a counting argument, that's not the case we're interested in, because that's the one with the higher power, and normally the idea is that the number of elements of order 11 and order 3 ends up adding up to the right number that you should end up with 5 cubed elements left over, which would be the normal, would have to comprise the elements of the normal subgroup for the CeLO 3 or CeLO 5 subgroup. The problem here is that there are 4 cases instead of 2. So it is true if you do the counting arguments with these two bigger numbers, you will in fact get that you're forced to have exactly 5 cubed, you're going to end up getting too many elements. So the counting argument does lead to a contradiction. But you should try and see that if you are in either of these two cases, when you do the counting arguments, you're not going to be able to force there to be exactly 125 elements left over. So the counting argument doesn't work well. So you're forced to start to deal in these two cases with needing to count elements G whose order divides 5 cubed, 125. The problem there is that given two CeLO 5 subgroups, they might intersect, they might not. We don't know. So counting arguments in these types of situations gets really complicated very quickly. So it starts to get much, much harder. So using method 1 in this case, where you have multiple numbers to work with, gets way too complicated way too quickly. And even then, sometimes the numerical examples no longer work. So we need a new method. And now we will describe the new method. So the new method is to look down here at 11. So there are 11 CeLO 5 subgroups. So now we're actually looking at method 2. G acts on the CeLO 5 subgroups by conjugation. Thus, you you get a homomorphism from the group to the symmetric group on 11 letters, which by Lagrange's theorem tells you that the order of G must divide 11 factorial, assuming that this map is injective. But of course this map has to be injective because the kernel is always a normal subgroup of G, and if we're going to assume that G is simple, that forces the kernel to be trivial, because if G is simple, the only normal subgroups are the trivial group or the full group. And if the kernel was the full group, then every element goes to the identity permutation, which means every group element fixes the CELA P subgroup, which means G inverse PG is equal to P, which would mean that P itself is a normal subgroup. So you have to be in this situation. Note here I run into a bit of a problem that I don't actually have a contradiction yet, because it turns out it's not clear if I have a contradiction. Is it the case that 4,125 divides 11 factorial? Well, this is a really big number, but it's worth pointing out the prime factorizations here. This is 3 times 5 cubed times 11. On one hand. On the other hand, I know we have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to, if I write it in increasing order by powers, get 2 to the 7th times 3 to the 5th times 5 squared times 7 times 11. And you see the problem. We do not have divisibility because on the left-hand side we have a 5 cubed, and on the right-hand side we have a 5 squared. So we do not have divisibility, and therefore we have a contradiction. So it must be the case that the kernel is not the identity map. So G is not simple. Ergo, there are no simple groups of order 4,125. And so that is the method. You let G act on one of the sets of CELA subgroups by conjugation. You get a homomorphism to a symmetric group. If the kernel were trivial, then Lagrange's theorem has a divisibility criterion. The divisibility criterion is not satisfied, therefore you have a non-trivial kernel. Therefore your group is not simple. The only mystery here is, how did I know to pick 11? Because it turns out there's no problem if you pick 25, or if I act on the CELA 3 subgroups, or the CELA 11 subgroups, so it has to be this choice. Note here I'm also being kind of careless. I'm assuming there are 11 CELA 5 subgroups. Obviously if there's only one, then you're already normal. I have a normal subgroup. Well, to explain how to make the choice, or to avoid the choice entirely, we'll talk about what's really going on. Given any subgroup H, you can let G act on the set of cosets as well. And this gives you an embedding from G into the corresponding symmetric group, where K is the index of G and H. And so if the kernel is trivial, then it must be the case that you have that the order of G divides K factorial. So suppose the order of G is P1 to the A1 pt to the AT. And notice that pi to the ai divides k factorial. This doesn't always happen, but one necessary or sufficient condition is if k is greater than or equal to ai pi. Why? Because then you would have pi, 2pi, 3pi, ai pi, all as factors in k factorial, and so you'd have ai copies of pi, so you would actually have pi to the ai. But know that that's only a sufficient condition. It might not be necessary. For small primes, there might be more stuff going on than that. For instance, 2. By this logic, you might be convinced that the smallest power you would need for 2 to the 4th to divide k factorial, it would look like you'd want k to be bigger than or equal to, or not 2 to the 4th, 2 cubed. It would be equal to 3 times 2, which is 6 factorial, but in fact, you already have divisibility once k is 4. But this does give a bit of a bound, and it tells you at least when k is bigger than the max of all these. Then that's when you're going to get g to divide k factorial. Certainly, at the very least, you can guarantee the inequality for the last prime. In the case when at is less than pt. Because there you can guarantee that this situation with 4 doesn't actually happen. And so what does that have to do anything? Well, the point is that if you need the index to be large. In order to avoid a contradiction. So remember, for any p dividing the order of g, the number of CELO subgroups is in fact an index of a normalizer. And so what you get from here is an inequality on the normalizers that you should get, and the size of each normalizer should be bigger than ATPT. And this is definitely true, at least when this largest prime when AT is either 1 or 2. So this is a good way to rule out small numbers. And if you're lucky and you rule out enough small numbers, you'll end up having a normal subgroup, a normal CELO subgroup somewhere. So as an application, we'll look at n equals 60 again, which was 2 squared times 3 times 5. And the values for n2, n3, and n5. Don't mind the dog hacking her lung up in the background. n5 could either be 1, 6, n3 could be 1, 4, or 10. n2 could be 1, 3, 5, or 15. So the point is, what is the smallest k such that 60 divides k factorial? Well, the smallest such k would be k equals 5. So we see this means by our method 2 that if g is simple, it has no subgroup, of index less than 5. And so if you include this information together, this would rule out these smaller numbers. So you start to see, if there's a simple group of order 60, start to see some information about what the CeLO 3 subgroups, how many CeLO 3 subgroups there are, and how many CeLO 5 subgroups there are. Granted, we already studied this case in detail earlier in the semester, but it's good to look at it from this lens and see how that proof could have been simplified using these methods. Of course, we aren't able to get rid of 15, but there's other techniques we'll learn that could have gotten rid of that, and then you would have had all the information you need. And so the textbook does something like this at the end of the section that we'll unfortunately have to skip, where they look at n equals 168, and they use all the methods from the section to get some information about the simple, if there was a simple group of order 8, what its structure would look like. And then they end up actually proving there is a simple group of order 8 and that it's unique up to isomorphism. So it illustrates some of the techniques in that area of if you're unable to rule out the cases, you start to get information about what that simple group must look like, and that allows you to actually prove the existence. The reason why I'm not going to go through the construction is because it gets very detailed. As they end up observing in the construction, the reality is actually constructing the simple groups takes a lot of effort and takes you out of the realm of group theory and into other areas of mathematics. As another example of our method, we'll try n equals 1503, which factors as, correction, 5103. 7 times 729, which is 7 times 3 to some obnoxious power. Is that the 6th power? So you see that n sub 3 is going to either be 1 or 7. N sub 7 is either going to be 1 or it's going to end up being 3 to the 6th. How do I see that? Well, because 3 to the 6th is 3 squared cubed. That's congruent to 2 cubed mod 7, which is 8 mod 7, which is 1. And if you take any smaller power of 3, you'll see that that's not congruent to 1 mod 7. So the only divisor of 3 to the 6th that's congruent to 1 mod 7 is the whole thing. It turns out you can actually do the counting argument method 1 in this case. But to illustrate what we're doing, I'm going to use the subgroup method again. What is the smallest factorial or smallest k? Such that n divides k factorial. Well, I mean, if we've got the 7, so we know it's got to be at least 7. But 3 to the 6th definitely does not divide 7 factorial, so it's got to be strictly bigger than 7, which means by our method, if g is simple, it has no subgroup of index less than or equal to 7, which already creates a problem right here. So can't have 7. Oh, and you can't have 1. Oops, you've run out of options. Contradiction. So it must be the case that g is not simple. Of course, if one doesn't like this approach, the alternative would have been to let G act on the CeLO 3 subgroups by conjugation. Give ourselves a homomorphism to S7 as a result, and then you immediately see the problem. If G is simple, you need to have the order of G divide 7 factorial, but that's not possible.